All right, guys, welcome everyone. Today we're going to have a very short lecture on dynamic programming. It's a very, very, very important must-know technique for software developers. So let's dive right in, okay? We'll start with a quick example of Fibonacci numbers. Fibonacci numbers are one of the most common sequences, well understood by a lot of people, very easily defined. It's simply defined as initialized as 1 for the first two numbers, and then simply take the sum of the previous two numbers, and that gets you your Fibonacci number. It's easily defined, and you can easily write it into any programming language. Here we see in one kind of programming language to say, if n is less than or equal to 2, return 1. Otherwise, simply make the recursive calls fn minus 1 plus fn minus 2. So what's the time complexity of this algorithm? Now, if you are new to analyzing the time complexity, you may think it's like n square or something like that. But if you have good experience with analyzing it, you can see that this has strands of exponential time in it here. And certainly, if we try to actually run it, just simply take the empirical evidence, we will see that actually it's very much exponential, and it goes well after some initial numbers. It really starts to grow very, very, very heavily, very quickly. And we have like 113,000 milliseconds. So that means almost 2 minutes just for 50th Fibonacci number. You can get to 55th, but most commonly 60th Fibonacci number cannot be computed using this particular technique here. And the chart also shows something very similar here. Now we can write it alternatively using the solution here. The code looks almost the same. We're just putting a different parentheses, I guess, in a way. We're just putting these brackets here. A1 is equal to 1, A2 is equal to 1. And for I is equal to 1, for I is equal to 3 to n, we simply keep adding those two numbers. So the code looks very, very, very similar. We notice that there's not a recursive call per se. It's just a loop, but that's what it comes to. And finally, we return the answer. And when we try to when we try to time this new solution, we see that actually just takes no time. It takes literally zero time here. So that's this particular time complexity for this alternative solution is nearly zero. It literally is linear. It takes order n time, and you can see just because it has a single loop that goes to from 3 to n here. So that is, and the trend line is also along the x-axis because you can't really time it at all. It's taking zero from the evidence here. Now, the thing that we may have to think about is, why does dynamic programming perform so much better than DNC? And the main difference between these two code samples here is that here you have recursive calls. Here you have simply an array sum, a single loop here. That much is clear. But what we have to observe more carefully is that here you have two recursive calls. And in fact, if we look even more carefully, we see that there is a lot of repetition in this code here that's recursively written. Fn minus 1 will then call Fn minus 2, and then Fn minus 3, and Fn minus 2 will then be called again. So there's a lot of rework being done again and again and again. Here, there is no rework at all. We simply compute the first one, the second one, the third one, fourth one, 23rd, 24th, 25th. We're simply using the previous ones here because we stored them into an array. So that is the key difference. That's the reason why the dynamic programming performs so much better than DNC here. And if we have to compare it, let's do a little formal comparison here. Divide and conquer, recursive calls, top calls down, and I'll explain again what that means. There is no intermediate results that are being saved in explicit storage. Now, of course, they're being saved by the programming language stack, but it's not an explicit storage that you created. And it only calls subproblems that are actually needed. In dynamic programming, it's also recursively defined technique, but it's not really invoked top-down. Bottom is called programmatically before the top is called. And you usually have some explicit storage, and you might solve subproblems that may or may not be actually needed. So let me go back one moment here and just help us see the order, the sequence as well in which we are computing it. Here you can see we are starting to compute the Fibonacci numbers. from bottom to top. Let's suppose somebody asks us for the 60th Fibonacci number. We just simply say, okay, we're going to start with the first, second, third, fourth, build up to 60th. Here we say, okay, you want 60th. Okay, we'll have to compute 59th and 52nd, make those recursive calls top down. And you can imagine many other kinds of recursive functions. Maybe let's suppose it was defined as like the n-5 or n-7. So in which case it would just call what's needed. So that is basically is what we mean by that the divide and conquer would call the subproblems which are actually needed, while dynamic programming would just build it from bottom to top, whether a certain part of the bottom is needed or not. So that's a quick comparison of dynamic programming versus divide and conquer. And when we look at the dynamic programming technique, the template has really 4 steps part here, and we use a mnemonic to help us remember what those 4 things are. The very first step, and in fact, the most important step, the critical step, is that you come up with a mathematical notation. So we call it the notation step, mnemonic here being n here, that the notation should be able to express any solution as well as any sub-solution for the problem at hand. Don't just think about the final solution, but also what you might have to create as an intermediate result. And another trick to remember here is you want to define the notation for the quantity that you are trying to optimize, even though sometimes the solution will ask us for something like what's the sequence, what's the direction, what are the steps you have to follow, etc. And we normally change that question ourselves to say, okay, what is exactly that we are being asked to optimize, minimize, or maximize? That particular notation is what we want to develop the mathematical notation around. So let's pay attention to this specific part carefully. First of all, your notation should be general enough. It should be able to express any solution as well as any intermediate solution, as we call the sub-solution for the problem. Secondly, don't try to think of the notation for the problem that's given to us in its most direct way, saying that, okay, find me the direction through this maze or something. Rather, think about the quantity that you're trying to optimize. Is it time? Is it number of steps? Is it the cost? And use the notation on that quantity. Okay. This will eventually come very naturally to us. But if you're new to dynamic programming, this is an important part that you want to remember here. You do want to see that the optimal substructure, the principle of optimality holds. That's the same thing we also talked about in the greedy algorithm lecture as well. Then come up with a recurrence relation, a recursive formulation that's going to relate the solution to its sub-solutions using the notation that you came up with in step 1. And finally, come up with the algorithm which will tell us the sequence, how you will build it from bottom to the top here. So the mnemonic NORA is quite helpful in this case. NORA for notation, optimality, recursive formulation, and the algorithm itself. So that's the dynamic programming. A very quick summary, really, in a at lightning speed here. It's a bottom-up table. It's a computation optimization technique in which you compute the solution bottom-up by synthesizing it from the smaller sub-solutions. It's a very, very, very useful technique for overlapping subproblems when you see that, hey, I'm computing, but it's just taking too long. Am I computing something same thing again and again? Then the trick then is to define your explicit storage, where you store your intermediate results so you can use them over and over again. That's really what I have here. Have fun, keep learning. The bottom line of dynamic programming is very simple, that you just, as a programmer, you just need to know this technique when you think that you're doing some recomputing again and again. Now, there's a small trick here that you may also be able to use memoization, and it's not a typo, it's not memorization, it's memoization, using libraries in Python, etc., in which it'll automatically remember if you made a function call, it'll just say, okay, yes, I remember this function was called with these arguments, I'll just return this thing. So that's a little bit of an implicit way of doing dynamic programming, but as a technique, Just try to define your explicit storage so you can use that result again and again. That's dynamic programming for you. Have fun. Keep learning, okay?